As ice melts, it goes from the solid state to the liquid state. This means that when a substance is in the solid state, all the molecules are set in rigid, fixed positions. But on the other hand, when it's in liquid state, they're all moving over one another because they're flowing freely. Disorder, therefore, is increasing since the molecules have so much more freedom of motion. Since they're moving from being rigid to be slipping over each other and going in any direction, that's an increase in disorder. Just common sense. Therefore, the delta S is positive because once the process is finished, the melting process is finished, there's more disorder. So the change in disorder is positive. Water vaporizing. Let's see. This is going from the liquid state to the gas state. And again, it's like the melting. In the liquid state, well, they're not really rigid, but they have less freedom of motion comparatively than when they're in the gas state. Because when they're in the gas state, they have free motion in all directions. Disorder, therefore, again, is increasing, and again, delta S is going to be positive. Cleaning your room. When you clean your room, your belongings go from a state of mess to being in the proper place, organized on shelves and in drawers. Therefore, your room, as the reaction of you cleaning your room goes to completion, your room goes from a state of disorder to a state of greater order, or from disorder to a state of order. Disorder is decreasing because order is increasing, so S is negative. Delta S is negative, I'm sorry. Folding paper into a paper airplane. This one's a little more complex. You have to think about it as in you are limiting the ways that the paper can behave when you fold it into a structure. So if you compare this one to number A, which is ice going from solid to liquid, from molecules being in fixed positions to a state of free motion, you can just think about that in reverse. And when you're folding the paper, it's kind of like you're freezing the paper from a liquid state to a solid state. More disorder, less rigidity to more rigidity, more order, more structure. Disorder, therefore, decreases because order is increasing because you're moving it from a state of more freedom of motion as a piece of paper to less freedom of motion because you're limiting the ways the paper can behave. So, therefore, delta S will be negative. Okay, this is an important table, which compares entropy, which we've been talking about, which is disorder, randomness, and it compares it to enthalpy, which is the amount of heat contained in a system. Once it was thought that spontaneous reactions were always exothermic, because for something to be spontaneous, there had to be a release of energy. It used to be that people thought for something to be spontaneous, it always had to be a loss of heat. But now we know that certain endothermic reactions can be spontaneous as well. For reaction number 2, according to the table, it says that there is an entropy increase. What entropy is it referring to? Delta S reaction, delta S surroundings, or delta S universe? Let's look at reaction number 2. It's endothermic with an entropy increase. It's delta H for the reaction is positive. It goes from a state of having less heat to having more heat. Disorder increases. Disorder of the surroundings of the system goes down. And the disorder of the universe, it depends. So for which of these three signs, these three delta S categories, these delta S columns, which one has a positive sign in it? Delta S universe, it's positive or negative, it's not there. Delta S surroundings, it's negative, it's not there. But delta S reaction, there's a positive sign there. So entropy increase must be referring to delta S reaction because that's the only one of the three columns that has a positive sign there. Let's look at reactions 2 and 3. Why can delta S universe be positive or negative for reactions 2 and 3? Reactions that are spontaneous always have a positive delta S universe. For example, reaction 1. On the other hand, reactions that are never